Hey everybody, welcome back to Mr. Murray's Mathland, and we're continuing our series of free response questions for the AP Calc exam, doing a little review of the different types. And we've hit all the major types in prior videos: velocity, table, differential equations. But there's often a sixth kind, which is what I call kind of a wild card or general calculus kind of problem, big ideas where they just kind of give you an equation and have you do a bunch of things with it that are classic calc questions. And one of those can often happen in the context of a piecewise function. So piecewise functions sometimes throw kids off a bit, so I'm going to do a video of nothing but different things with a piecewise function. So here we go. Let's just jump in here. These are all the various things I've seen throughout the years. It's not guaranteed to be there every year on an AP exam, but it's certainly things I've seen before on FRQs, so just good to be comfortable with these. So we're given this piecewise function below, and the first thing we're asked is f continuous at x equals 2? And notice 2 is the sort of borderline or transition x value where it changes from this graph to this graph. And it wants to know if it's continuous and says use the definition of continuity to justify your answer. So if you're working on a multiple choice and you're just trying to move fast, it's essentially just seeing if these two things have the same y value at 2 to see if they're connected. But when it says use the definition of continuity, you're on an FRQ, you want to show some calculus here. So the definition of continuity is showing that the limit exists as x approaches c, whatever that c may be. In this case it's 2, and that means also showing that the y value exists at c and that they're the same, right? So the visual of this is making sure the limit exists means the limit from the left equals the limit from the right, and it can have a hole, but that wouldn't be continuous, so we make sure it has a y value at that point and that y value is the same as the limit. So they're all going to the same place. That's essentially it. It's just taking a concept and making it a little fancier, being a little formal. So let's just go. Let's do this. No particular order here, but you might say, let me see if the y value exists, and you can see that x is greater than or equal to 2 at the cosine of pi x over 6. So we're going to use the second equation to show f of 2. So you're going to plug 2 into that, and you get 2 pi over 6, which you may already be reducing in your head to cosine of pi over 3, and that is equal to 1/2. Hopefully you're good with your unit circle values. And now let's check the limit. And when we say the limit, that means you've got to make sure the limit from the left equals the limit from the right. So the limit as x approaches 2 is the x value we care about from the right. I guess I'll do the right first. And the reason I'm going to do the right is because I essentially already did this a moment ago, because for x values greater than or equal to 2, you're using this function. And so I use that when f was equal to 2, and for my limit, I'm doing the same thing, from the right. You're essentially plugging into that, and you're getting the same cosine of pi over 3, which is 1/2. So you may think that's obvious, but you still want to show it. You don't want to leave any doubt in the graders' minds here. And now the big thing, the limit as x approaches 2 from the left, that's where you're going to use that other function for x values less than 2. I'm going to substitute 2 into there. As x approaches 2 from the left, you're going to be getting e to the 2 minus 2 over 2, which is e to the 0 over 2, and e to the 0, or anything to the 0, any non-zero to the 0, is 1. So they're all equal to 1/2. And so make sure to actually answer the question. Don't just leave a bunch of work. It says, is the graph continuous at 2? And yes, f is continuous at x equals 2, and if I really want to spell it out and make sure I get that credit, since the limit as x approaches 2 on f is equal to f of 2. And there you've said everything that you can possibly say, and you got credit. Okay, move on to the second part here. Same piecewise function, write an equation for the line tangent to f at x equals 5. So again, this is just sort of a classic calculus question. Write the equation of a tangent line. So we need two things. We need the point of tangency, and they only gave us the x value. So the point just comes from plugging 5 into the function. And f of 5 is greater than 2, so you're going to be using that second piece. So f of 5 would be substituting 5 into that, and 5 times pi over 6 gives you cosine of 5 pi over 6, which technically doesn't need to be simplified on an FRQ, but you know, why not here for practice here? That is going to be quadrant 2, where cosine is negative, and root 3 over 2. And for our slope of our tangent line, well, that's where you need f prime of 5. And the problem here is you don't have f prime, so we have to create f prime. So we're just talking here, let's do a little derivative of a piecewise function. If that's f of x, f prime of x will be, and even though I really only need the derivative at the second piece, we'll just do the derivative of the whole thing to practice. The derivative of e to the 2 minus x over 2, the derivative of e to the anything is e to that exponent, and then chain rule multiplying by the derivative of that exponent. And the derivative of 2 minus x is negative 1. So you're going to get negative e to the 2 minus x over 2 when x is less than 2. And for the derivative of the second piece, the derivative of cosine is negative sine of that same argument, pi x over 6. But again, chain rule, right? Chain rule, got to multiply by the derivative of the inside, so that means you're going to get this coefficient of pi over 6, or negative because of that cosine derivative rule. And that would be for x values greater than 2. Notice I didn't include equal to 2 because I'm not sure that the derivative exists at 2. That would be a different thing altogether I'd have to check for differentiability. But this, I just want the derivative at 5 for my tangent line, and that would be using the second piece. So negative pi over 6 sine of 5 pi over 6. And again, if you are on the FRQ, you could leave that as a slope. That does not need to be simplified. It's all numerical, so you could stop there. For practice here, the sine of 5 pi over 6 is quadrant 2, where sine is positive, and the sine of that reference angle, pi over 6, is 1/2, so you're going to get negative pi over 12. That's your slope. So your tangent line could be written as y plus root 3 over 2, right? Because again, this was the point of tangency, was 5 negative root 3 over 2, equals the slope of negative pi over 12 times x minus 5, if you want to use point slope form. And again, either of those, the y coordinate, you could have left cosine of 5 pi over 6, or this slope of negative pi over 12, you could have used this unsimplified version. On an FRQ, you can save yourself time and not simplify things. Part C. So again, same piecewise, but now we just did a derivative. Now you're doing an integral. Evaluate this integral from 0 to 4. And this is fairly common to ask this on a piecewise function because notice the limits of integration. We're starting at 0 and integrating until 4. So 0 is less than 2. So you're beginning by integrating this portion, right, of the piecewise. But you're ending at x equals 4, and x equals 4 is beyond 2, so you're ending with this function. So you're kind of spreading that integral across these two functions, which means you've got to break it up and make two definite integrals. So the first one from 0 to 2, that's the x value where the equation changes to the other equation. So that will be, I'm going to integrate e to the 2 minus x over 2 dx, don't forget your differentials, plus from 2 to 4, it's going to switch to cosine of pi x over 6 dx, and I have to evaluate those, and I've been approaching this from a non-calculator standpoint, so let's work on our integration, right? Okay, so antiderivatives, doing the fundamental theorem of calculus here, getting this antiderivative of e to the 2 minus x. Well, we just did a derivative, same idea, antiderivative of e to the x is e to the x, so we're going to get e to the 2 minus x still over 2. But again, because of chain rule, you have to divide by that derivative of -1, so you're going to get a coefficient of negative. And you could use U substitution if you feel it's necessary to sort out that one little negative, but often that's an easy little adjustment you can make without having to do the whole process. And similarly here, the antiderivative of cosine of pi x over 6 is sine of pi x over 6, but again, because of chain rule, right, pi x over 6, you would have to divide by that pi over 6, which really means we're going to multiply by 6 over pi. Again, you could use U substitution to sort that out for you and force you to put that 6 over pi there, but that's usually a simple thing we can adjust right on the spot. And so now let's go. We got these limits of integration. We can't stop here. Let's substitute in the fundamental theorem of calculus. The top limit goes in first, so you're going to get e, or negative e to the 2 minus 2. I'll try to show every step here, but if you're working, you can skip some steps. Minus substituting 0 in, and so minus that negative e again is going to give you plus e to the 2 minus 0 over 2. And then we're adding our result from a second definite integral. So I'd be substituting 4 in first. So plus 6 over pi sine of 4 times pi over 6, which is going to reduce to 2 pi over 3, minus 6 over pi sine of 2 pi over 6, which is going to reduce to 1 pi over 3. But I just like to make this point again that now you've substituted those in. This is all one big numerical answer at this point. And I like to give the idea that if you could plug it into a scientific calculator and type that all in, then that's the sort of answer you could leave as a final answer, unsimplified. You could stop right there, save yourself time, and move on to the next part. I'm going to simplify it for practice with doing these things, but on a real FRQ, I would stop and just move on. But here we go here. It's a little practice, right? 2 minus 2, that's e to the 0, which is again 1, so we're going to get negative 1/2 plus e squared over 2. And what's kind of nice here is that when you do simplify those, that's sine of 2 pi over 3, like we said, and sine of 2 pi over 3 is positive root 3 over 2, your quadrant 2, where sine is positive, minus 6 over pi times sine of, that's pi over 3, and sine of pi over 3 is quadrant 1, where everything's positive. So these two values actually cancel each other out. So, if this were a multiple choice question, for example, you would see a simplified answer. You would see negative 1 over 2 plus e squared over 2, or perhaps written as one fraction, since they have the common denominator, maybe e squared minus 1, something like that. But that does not need to be done on an FRQ. Okay, so integrating a piecewise, taking derivatives of piecewise, we've done those. And now part D, find the average rate of change of the function over the interval 0 to 3. Average rate of change, right? Average rate of change, that's essentially just average slope. That's the slope of the secant line, right? That's easy stuff. y2 minus y1, f of b minus f of a over x2 minus x1, b minus a. So in this problem, you might like to just find them separately first. It's kind of up to you. F of 3, we're going from 0 to 3. So f of 3 is, again, substituting into the bottom one, cosine of 3 times pi over 6. Again, you could stop there, but that's cosine of pi over 2, and cosine of pi over 2 is 0. Kind of nice review of the unit circle. F of 0, the other x value, that would be substituting into the first piece, So 2 minus 0 over 2, and that's just e squared over 2. So there's your 2 points, and so now your average rate of change over 0 to 3 is y2. Well, I kind of went in the opposite order I normally like to, but it doesn't really matter as long as you're consistent, over 0 minus 3. And so you're going to get actually negative e squared over 2 over 3. Or if you were on a multiple choice, that would be expressed as negative e squared over 6. Okay. So now let's move on here. Last part, for some value c, where c is between 0 and 3, is it guaranteed that f prime of c will equal the average rate of change you found in part D? So that average rate of change, in case we need to refer to it, that was negative e squared over 6. Okay, but they're really not asking you to do much with it. They're just saying, is it guaranteed that f prime will equal that value at some point? So this is a popular kind of thing on FRQs. If they're asking you if a function is guaranteed to equal a particular value, oftentimes it's either the intermediate value theorem or the mean value theorem. And in this case, you found the average rate of change using f, and they're asking you about f prime, its derivative, equaling that particular thing. And that is the mean value theorem right there. That's classic mean value theorem stuff, which is the idea that f prime of c must equal f of b minus f of a over b minus a, right? The instantaneous rate of change must equal the average rate of change. The tangent line slope must equal the secant line slope at some point in that interval, if, and that's only if this is true though, if the mean value theorem applies, which means f is continuous, which we've already proven, and differentiable. And that's really the thing we haven't yet addressed. So this answer is going to be yes if I know it's differentiable, but let's go here. Let's approach this. So step one, f is continuous. We've already shown that, but you might refer to that to make sure you sort of verify that it's been addressed. The thing we have to know now is f differentiable? And that's what we're going to find, and that is essentially, you know, proving continuity on f prime. And so that same process we did in part A to prove continuity, I'm going to do that on f prime. Now I've already found f prime back in part B here, which is why I'm just being lazy and scrolling back. But you would just be looking on the piece of paper to your right or left, you know, on the AP exam. So here we go. Here is this derivative. And so there is my derivative. Now I just want to see, very similarly like I did, does the limit as x approaches 2 from the left on f prime equal the limit as x approaches 2 from the right on f prime? In other words, does the slope from the left equal the slope from the right on f? That's what you're essentially seeing to make sure there's no cusps. We already know it's continuous, but if they're not jammed together smoothly, that's going to create a cusp, and that's not differentiable. So it's really a matter of just plugging 2 into these f prime values, right? So you're going to get negative e to the 2 minus 2. So again, that's going to be e to the 0 over 2. That's going to be negative 1/2. That's the slope from the left at 2. And now the slope as x approaches 2 from the right would be substituting that into that trig function. And you may already start to see that I don't think this is going to work out to be negative 1/2, but who knows? You plug in 2, you get 2 pi over 6, which is pi over 3. And again, just to simplify and to verify in your mind, sine of pi over 3 is root 3 over 2. So we're getting negative pi root 3 over 12. And that is not equal to negative 1/2. It's fairly close if you look at the decimal. It's something like negative 0.4, but that's not negative 0.5. It's definitely not equal to negative 1/2. And so since these are not equal, f is not differentiable. So the mean value theorem, MVT, and it is okay to abbreviate, mean value theorem does not apply over the interval 0 to 3, because that 2 occurs within that interval. And so finally answer the question, because it said, is it guaranteed? So no, it is not guaranteed that f prime of c equals the average rate of change from D. Right? And so just make sure you answer the questions that they actually ask. You know, don't just leave it up to the grader to guess. So another video about FRQs. If you have any questions, feel free to ask. Otherwise, keep working hard, and we'll see you later, kids.